Welcome to the section 3.5 notes. I'm going to have you pause the video and work through this warm-up question quick, and unpause it and see how you did. So we can remember from 3.4 that our arc length is our central angle in radians times our radius, or our arc length is our central angle given to us in degrees times 2 pi over 360 times r. And since I'm given my angle measurement in degrees, I'm going to use this one. Okay, so our radius is going to be 197 divided by 2, since we are given the diameter. So radius is 98.5. So our arc length is 60 degrees times 2 pi over 360 times 98.5. I know that 60 times 2 is 120. 120 over 360 simplifies to 1/3 times pi times 98.5. So an exact answer would look something like this. But my estimated answer, if I plug this into my calculator, is going to say that my arc length is about 103.15 feet, because we were given the label feet. All right, so today we're going to be talking about velocities, both linear and angular. So if a Ferris wheel says that one trip around has to take 20 minutes, and you're asked how fast was the rider traveling, there's a couple of ways you can answer it. Generally, most people think in linear velocity because that makes the most intuitive sense. So that's how fast or how far you can go in a certain amount of time. So how fast you're going. It's going in a straight line, which is why it's called linear. Now, since it's going in a straight line, that's when we're traveling on the ground typically. That's why it might not be the best measurement if we're talking about something going around in a circle, because in a circle, obviously, it's not a line. That's when we might want to use angular velocity. So angular velocity is given as the amount of a central angle through which the rider travels over a given amount of time, and it's measured in degrees per minute or radians per second. So linear measurement, the linear velocity is given with a linear measurement over a unit of time. Angular velocity is given with an angle measurement over a unit of time. So again, typically, angular velocity is when we're going around a circle. So in the original statement, the wheel goes one full rotation, which we know is 2 pi radians, in 20 minutes. So if I want to know what the angular velocity is in radians per minute, I know I go 2 pi radians in 20 minutes. Okay, I simplify this fraction. This simplifies to pi radians in 10 minutes. So my final answer would be pi over 10 radians per minute. I kind of just treat those labels as if they're part of the problem, and at the end I know I have radians on top, minutes on bottom, radians per minute. If I want to know the angular velocity in radians per second, well, I already know that I have pi radians per 10 minutes. I'm going to treat this like a fraction, and like labels, I'm going to have minutes. 1 minute is 60 seconds. So I can kind of treat this as minutes canceling out, and that leaves me with pi radians on top. Pi radians times 1. 10 times 60 is 600, and we're label it is now seconds because minutes canceled out. So I have pi over 600 radians per second. So every second we go pi over 600 radians. So angular velocity, we use the Greek letter omega, not W. I'm going to write my omegas something like that, kind of like a 3 with a little loop in it. That's when the motion of an object is measured in angular displacement, so an angle measurement per unit time. So omega is equal to theta divided by time, divided by t. So for these first two problems, a point on a circle rotates through 3 pi over 4 radians in 3 seconds. Give the angular velocity in radians per second. I go 3 pi over 4 radians for every 3 over 1 over 3 seconds. Okay, that's what omega equals. When I'm dividing by fractions, that tells me that I am actually multiplying by its reciprocal. I'm going to leave radians and seconds alone because I know radians goes on top, seconds goes on bottom. So this is 3 pi over 4 times 1/3. 3's cancel off, and I'm left with pi over 4 radians per second. Number 2, if a point moves through 60 RPM, give this angular velocity in radians per minute. I know that 1 RPM, 1 revolution per minute, is 2 pi radians. So 60 RPM is going to be 2 pi times 60 radians. So if I want to know the angular velocity, I know that I'm going 2 pi r, or 2 pi, times 60, which is 120 pi radians every 1 minute. I'm asked for radians per minute, so I can simplify to just 120 pi radians per minute. I'm going to leave pi in my answer all the time, unless it says it wants a decimal. Don't give me a decimal. Keep it as 120 pi. It's a nice exact number. So for these ones, these are all basically the exact same thing, just written slightly differently. So linear velocity is the arc length divided by time. How far did you go divided by how long did it take you? Okay, this is kind of like, so I envision running around a circle. If you were able to cut the circle and straighten the whole thing out, how far along that circle did you run, which is now in a straight line, divided by how much time did it take. We know that S is equal to our radius times our angle measurement, so I could replace that in the numerator there. So velocity could be the radius times the angle measurement given in radians divided by time, or we just also showed that omega is equal to theta divided by t, which I have omega divided by t right there. So I could also say velocity is equal to the radius times omega. So you've got options. You might use all of these. You might use some of these. Depending on the question, some might be easier than others. So remember that v is our linear velocity, s is our arc length, t is time, r is radius, theta is our central angle, and omega is our angular velocity. So if a point on a circle with radius 5 centimeters rotates once every 2 seconds, find the linear velocity. So I've got kind of 3 options. I've got this one, that one, or this other one. That was a terrible omega. I got to be better than that. So that wasn't much better, but I'm going to move on anyway. So I've got those 3 options. You want to use the one where you know information. So I know that I have a rotation once every 2 seconds, and I know I have my radius. So if I rotate once every 2 seconds, that's 2 pi every 2 seconds. So that tells me my omega is pi radians per second. And I know my radius is 5, so I'm going to use this one right here. So my velocity is going to equal r, which is 5, times pi. Now my linear velocity, I know this was 5 centimeters times pi radians per second. I basically drop the radians, and I end up with centimeters per second. Okay, my linear velocity is 5 times pi centimeters per second on the outer edge of that circle. Again, if it wanted a decimal, it would tell you, then you would round. But otherwise, you just leave it as 5 times pi. Make sure you have a correct label. We're not talking radians per second anymore because we're actually looking for that linear distance that traveled, which is no longer an angle. So that's why we can't have a radian measurement there. So number 4, a bicycle wheel with radius of 13 inches turns at a rate of 3 radians per second. Find the distance traveled by a point on the tire in 1 minute. So I know my radius equals 13. I know omega is 3 radians per second. I want to get this in terms of minutes. So I'm going to multiply that by, well, I have 60 seconds over 1 minute. So if I can go 3 radians in every second, that means I can go 180 radians every minute. So if I want to find the distance traveled, there's a few ways you can go about doing this. I'm kind of just putting things together this way. You can go through a different way. You should still end up with the same answer. So what I'm going to do is I'm going to say that I know omega, I know what my radius is, I can find my linear velocity and then multiply by the time, or what I've done here is I figured out that I know this formula, right? I know that omega is equal to that angle divided by time. I figured out what this piece is, so I can figure out my my angle measurement, multiplying both sides here by t, and I've got that theta is going to equal 180 radians. I almost said degrees. Okay, that's just based off of this right here. Multiply both sides by minute. If I know that, I know I've got 180 radians, and I know that I'm going to use the formula S equals R times theta. S is equal to 13 times 180. If I take 13 times 180, I'm going to get 2,340. I got to think about what my label is. My radius is in inches, so this is in inches. So the distance traveled was 2,340 inches in 1 minute. You could convert that to feet if it asked you to convert it to feet, in which case you would just divide by 12. And I know this problem, I kind of went back and forth between two different ways of solving this. I hope that didn't confuse you too much. I'm going to do another quick way without doing conversions at the beginning. So I could say that my velocity equals R times omega. Linear velocity was 13 times omega. I'm just going to use that 3 radians per second. So my linear velocity tells me we're going 39 inches per second. Okay, but I know I'm going for a minute, so I would just take this times 60. You'll still get that same number right there. Multiple ways to do pretty much any problem in math, which is kind of cool, kind of annoying sometimes. Number 5, a circular saw blade with a radius of 5 inches rotates at 600 RPM. Find the linear velocity of the point on the outer edge of the blade in inches per minute, then go to miles per hour. So again, radius is 5, omega. Okay, I know I go 2 pi, that's one time around. I'm doing that 600 times. So 2 pi times 600 radians per minute. So if I'm going to find my linear velocity, I know my radius and my omega. I'm going to use that formula. So I've got 5 inches times, that's going to be 1200 pi. So my linear velocity, 5 times 1200 is 6,000 pi, and then it's a linear velocity, so it's the unit of measurement for distance, which in this case is inches per minute. Okay, and linear velocity is 6,000 pi inches per minute. Now we want to convert that to miles per hour. So I'm going to write out this entire step all at once, and then we're going to simplify. So if I'm looking at 6,000 pi inches per minute, I'm going to put 6,000 pi inches over 1 minute. And then I'm going to focus on one of the labels first. I'm going to focus on minutes to hours because I think that one's a little bit easier. So if I want to change from minutes to hours, I know that 1 minute has, I almost went to seconds. That would have been the wrong way to do that. So I know that there are 60 minutes in 1 hour. So I make sure that I have minutes on the top and bottom, so they're going to cancel out. So that gives me to all my hours. Now, minutes are gone. Now I also need to do inches to miles. So I'm going to start by inches to feet. I know that I have inches on top already, so I need to have inches on bottom. There are 12 inches in 1 foot. Okay, so that would, if I divided by 12, that would tell me how many feet I traveled, but I need to, need to know how many miles per hour. So to go from feet to miles, feet is already in the top, put feet in the bottom, miles in the top. 1 mile is 5,280 feet. So at this point, inches are going to cancel out, feet are going to cancel out. I'm going to be left for my labels with miles per hour. Now I just do all the top times all the top, all the bottom times all the bottom. So this would equal, well, I'm going to just kind of put a pi at the end there for now. 6,000 times 60 is going to be 360,000. On the bottom, I have 1 times 1 times 12 times 5,280, which is 63,360. Okay. Now we simplify our fraction. If we use our school calculator, we've got our math enter button. Ignore the pi when you're plugging that in. So 360,000 divided by 63,360. Math enter. That gives me 125 over 22. There's your pi. Miles per hour. That would be our exact. If I wanted to know a decimal round to a specific amount, I would plug this into my calculator and say that that is approximately 17.85 miles per hour. Okay, so here's my exact answer. There is a rounded estimate. There is your assignment for you to work on later. Hope everybody has a great day. Make sure to bring questions to class.